since the expression for A2 contains only the variable b over h, both b and h having the dimension of length, hence it is dimensionless. A2 may appear to be an arbitrary entity since it has no physical or geometrical significance. However, also it has been artificially derived. We can mathematically find the conditions under which it is a maximum. Q will be a maximum when A2 is a maximum, and consequently M a minimum. That's what we want to find, a value Q which is very high. If we have a very high value of Q, then we will have a minimum of material. We see there are many possibilities to construct an arc. In the case for the maximum, you see it's an arc with the value b over h. It is 0.5. It is most economical for use of material, but you can see it is a very, very unstable arc. The other one, what you see on the right side, it is very stable, but the value A2 is not so high. So it needs very much material to construct such an arc. But from the viewpoint of material requirement, it would be the best arc if we use b over h for the value 0.5. On this picture, you see all the motions of an arc. Some of the motions, you see, have a restoring forces. Motions, and also we have motions with restoring forces, dipping, or with restoring moments, pitching and rolling. There are back movements with initial behavior. The very important thing for the floating stability is the rolling motion. We use the law of nature for floating bodies. This law is discovered by Archimedes. It's very old, you see. The amount of liquid displaced by a body floating in its weighs as much as the body. Here you see two positions of an arc. On the left picture you see a normal situation, and on the right side you see an arc with a tilt angle alpha. And there are two forces which we can see: the force of gravity, that is G, and the force A is a buoyancy force. Both forces are equal, and the point where the gravity is going on is the gravity center, and the other point is A is going to the gravity center of the displaced water. Here you see once again an arc with a tilt angle A alpha. We need for the calculation a few distances and coordinates for the floating stability. You see the meter center above, and you see the center of gravity of the complete ship, and the center of gravity of the displaced water. G is the force of gravity, and A the buoyancy force, and G multiplied by the distance rho, that is the restoring moment. It's a very important moment which brings the arc in the normal position. When I started to calculate the formulas, I had the idea it needs only a good evening and I'm ready. But when I started, I saw I have to use all the different positions of the arc. And so I had many formulas for the different positions of an arc. Now let me come to the floating stability. Here you see in triangle, it's not important to know all the equations, but let me come to the solution. This formula, number 6, is a very important equation. It's a central equation for calculating the floating stability of any box-shaped ship. And you see on this formula there are also only related values. And that means the floating stability depends only on related values. B over h, the ratio of breadth to height. The next one is the ratio of center of gravity to the position of height. And the third one is the ratio of draft to height. And the very important point is the ratio of distance of the forces couple A and G to breadth. What are the important things here for the floating stability? We have two cases for an arc. The stable condition is if the meter center is above the gravity center SG. It means that the value rho over B must be greater than 0. And the unstable condition is if the meter center is below the gravity center SG. It means if the value rho over B is less than 0. The measurements for an arc, we can say the volume is a given value for Noah's ark, a given value for the purpose. Now what we have to calculate is the value, the right value, the optimal value, B over H. It must be an optimal ratio for economical use of material and good floating stability for the rolling process. And another important ratio is L over H must be an optimal ratio for stability concerning waves. It means the pitching moving. Number 1, I have done the B over H calculation and will demonstrate it now. L over H remains to be done. Now we come to the solutions of the equations and we see it in the diagrams. On this first picture you see an arc. It's a box which width is 5 times its height. And you can see it is a very stable condition. It is very good on the water. And that's what the curves shows also. All the values rho over B are positive. So we can say all kinds of arcs are stable. Let me give an idea about the parameter for the curves. H0 over H. It shows us how many percent of the arc are into the water. What is the displaced water? If this value is 1.0, what do you think what kind of ship it is? It's a submarine, yes? And if we would have the value 0.01, it is in a polystyrene arc with only 1% is in the water. I have calculated all the values because I want to see the behavior of these parameters. Now let's have a look to a square arc where B over H is 1. We see the gravity center in this way is 0.3. It means the gravity center is 30% of the height of the arc. You see in this case for angles from 0 to 60 degrees or 45 degrees it is stable, and on the right side we see there are parameters when it is unstable. If the gravity center is very high, you see also the consequence in the floating stability curves. So it is more unstable than the other way. Now on this picture you see a flat-shaped box where b over h is 0.5. And you see in this case what we can feel, what it is, all the arcs in this way are unstable. So it's not good to construct an arc in this shape. Now let's come to another very important and interesting value for calculating the floating stability. I have defined a value ES. It is the integrated floating stability. It is a function of the level of the gravity center and depends from the value b over h and also from the value h0 to h. We have to integrate the formulas. I have done it for the angles 0 to 90 degrees. For different parameters h0 to h and for different high levels of the gravity center. We find a set of curves for various in a diagram with h0 by h is constant. What we see is on these three curves here, the less yg over h, the better is the stability. And that is the function f1, I have named it here. So we have a problem if we want to construct an arc which a minimum of material, then the stability is not good. But if we use a very stable arc, then we need a maximum of material. What to do? We combine both parameters and optimize both parameters by a computer program and find the optimal value. And that's what I have done. I have combined the function f1 and the function f2 by multiplying. So we find a new curve with the name f3. The maximum of f3 shows the arc with the best ratio b over h. The solution you see here. In this diagram we find the integrated floating stability multiplied by q as a function of b over h. Here in this picture you see the relative depth of immersion, 30%. It's a realistic value for the arc. And another important point is yg over h, 0.28, the relative height of center of gravity. Then if we use this special value, I assume that it would be a good value for the arc. Then we find the optimal value b over h, 1.667. This is the same value as we see in the Bible. Let's see the stability curves of this special b over h. We see all the curves show that rho over h, the curves are all stable. We have stable conditions. So we can say we have a good stability and also economical use of material. You are familiar with the Gilgamesh epic from the Babylonian, and on table number 11 it is written, "The ship that you will build shall have the following dimensions. Its length and breadth shall be equal. Its walls were each 120 cubits high. The four edges of its decks were each 120 cubits long. I designed its rooms and assembled them together. I installed 6 intermediate decks. I divided it up into 7 floors. And that's what we see here on this picture from the Gilgamesh Ark. It is a cube, and you see the 7 decks. Now, after you have seen the formulas for floating stability, you can say if it is a good ark on the water or a bad one. And you see, you can say it is a very bad ark. Why that? The gravity center is very high because there are 7 decks. And you see also it is a cube. And so it rolls all the time in the water. Now let me come to the conclusions. Now, several thousand years after the construction of the ark, using laws of nature and high-speed computers, we arrive at the most economical and most stable condition for the ark. We can say the best fit in economy and stability that we found is precisely those dimensions described in the Bible. This clearly refutes the assertion by many theologians that the Babylonian Gilgamesh epic predates